Okay. Good afternoon to dear course participants. That lecture topic today is remote sensing and GIS applications in soil resource assessment. As we know that soil information is very much required for to assess potential of soil for various uses, for example agriculture, forest, plantation, urban planning, or many more applications are there. Soil informations we need for assessing land degradation, mainly soil erosion. For watershed planning, we require this information for soil and water conservation. To study soil fertility and soil productivity, soil information is required to assess soil quality, soil health, and to study also related to climate change, how much carbon is stored in soil, that we know as a soil carbon stock. It is because soil also governs the crop water requirement, because soil holds the water. So for estimating crop water requirement, and also requires for the urban land use planning. So you can see that there are various applications are there for soil information. So in this lecture we are going to discuss in detail how we can generate soil information. So you will see that I will discuss the how we can use remote sensing satellite data for mapping of soil. What is the basic concept behind that, and what steps we do that one. Second is that we once map is prepared, then we can assess the potential of land for land use planning. So I will also deliberate on land evaluation. Third point I will cover, that is how we can use remote sensing data for mapping of our degraded lands, because continuous use of lands are inviting the degradation of these soils, and can we map these soils with remote sensing data. And fourth point we will discuss, that is hyperspectral remote sensing data in mapping of salt affected soils. And at the end I will also touch the points on how we can use digital soil mapping techniques in mapping of soil nutrients and other soil properties. So first comes, that is what do we mean by soil. Sometimes we see a geologist says that is the soil is the upper earth crust as a loose material. Agriculturists call soil or say soil provide nutrients to plant vegetation, and it provide the physical support to vegetation. And for others they say that is the soil also used as a building materials and for urban infrastructure and other services. So if we see that is the soil, if we take the composition of soils, so we can say that 45% is mineral matter, which comprises of sand, silt and clay. 5% organic matter, because you know the organic matter or humus is very important for binding those soil particles and imparting the chemical characteristics and physical characteristics of soil. And 20-25% is air, and 25% is, you can say, the water. That is the composition. When you are saying the mineral sand silt clay, you can say they are depends on the size, and the smallest soil particles is clay particles, which is less than 0.02 millimeter. And this is called clay particles, and clay particles are most important particles which have the negative charge, and because of that it hold the nutrients, absorb the nutrients on this surface. It has high specific area, that's why it's hold the water you get the properties of water holding capacity. And clay humus complex is also makes the complex with the clay humus, and to preserve the organic matter or to contain the nutrients. So that's why soil is a sand silt. It is composed of sand, silt, clay, and clay is important constituents of the soil. But what in soil mapping we define soil, uh, we consider soil as a natural body, three-dimensional body. You are seeing in the picture, that is, we are taking the vertical section where you are getting various horizons. Top layer is called O horizon, which is more blackish in color, generally found in the forest soils. Otherwise, A layer, top layer is called A layer, A horizons, that is agricultural layer. B is the subsurface layer, where mostly the roots are concentrated, and C layer is derived from the parent material, or that is the parent rock, weathering of the parent rock, and this is a C is called as a parent material. So what the soil is developed is over the sea, over the parent material, and the properties of these soils are controlled by integrated effect of climate, land use, land cover, and parent material. These are the property which control the basic characteristics of the soils, and it is conditioned by topography over the period of time. This is the standard definitions a soil surveyor consider. Sometimes we are also interested to know where I can get the soil map. So there is a soil survey organizations in our country. One is, that is the National Bureau of Soil Survey and Land Use Planning, which is located in Nagpur, a ICR institute, which have the mandate of preparing the soil map of the country, and the entire country has been mapped at 250,000 scale, and 50,000 scale, which is required for the district level planning. For some of the states it has been completed, and some of the states are remaining and is on process. Another department of soil mapping is Soil and Land Use Survey of India, New Delhi. Earlier we used to call it All India Soil and Land Use Survey. It prepared the 1 is to 50,000 scales, 20,000 scales, and very detailed 4,000 scale map. And related information also we are getting ISRO Bhuvan portal as a geomorphology map 50,000, digital elevation model 50,000 scales, land use land cover 50,000 scales, and also available at 1 is to 10,000 scale for detailed planning. In the remote sensing, we are depends on the spectral characteristics, because the remote sensing we deal the spectral signature to interpret the object. And in the vegetations, that is the we are getting a very peculiar characteristics of vegetation, spectral characteristics of vegetation, where you are seeing that is the in a red radiation, red wavelength region, it is absorbed, and in near infrared it is reflected. But in case of soil, if you see the reflectance characteristics, it increases as the wavelength increasing. Therefore, it is you are not getting very contrasting features for different composition, but you are getting the reflectance governed by soil texture, organic matter, soil moistures, and the salt content present into the soils. They govern the reflectance characteristics. And from the remote sensing data, you are getting the surface reflectance, but we are also interested to know about the subsurface soil, and because subsurface soils governs the properties of the surface soil, therefore interpretation of subsurface soils with remote sensing data, it is not possible, or you cannot interpret the subsoils directly. So for a picture I show you, I want to prepare a soil map of this area where it is hills and covered with a vegetation. If you take the reflectance characteristics of this one, then you will get the reflectance of your vegetation, not the reflectance of soil, because soil is covered with vegetation. So in the natural forest cover, or where the throughout the year there is vegetations remain, soil mapping with the correct reflectance characteristics is almost not possible. Because if we I see in this one, I remove the I take the cross section in this area, then I am getting swirl information, because swirls are darker in color, having stones also within that one, or coarse fragments within that one. So I can say that directly remote sensing data cannot be interpreted for the mapping of soil. So in case of standard soil mapping based on reflectance characteristic is not possible, as we have to map subsoil or soils of the root zone beyond and sometimes up to the parent material, then we cannot get only the information from the reflectance. But in case of degraded lands, which affect in this case degraded lands, the surface of the soils are get affected, and they give the very peculiar characteristics of the spectral characteristics, and I can say this can be directly observed by the surface reflectance and can be mapped. So standard in general soil mapping, we cannot map with the direct based on reflectance, but in degraded soils we can map directly based on the reflectance characteristics. Uh, we see that is the what kind of soil survey we carry out. There are standard soil survey scales are there, because if you want to prepare a map, first you have to find out what scale map you want to prepare, or what scale soil information you want to generate. One is that a reconnaissance soil survey, which uh, which we call 1 is to 250,000 scales, and the remote sensing data sensor resolution is a coarser. We can use list 1 data, list 2 data, or IRS AVIF sensor data. For semi-detailed survey, the standard scale is 1 is to 50,000, and we can use Indian remote sensing satellite data list 3, Landsat TM, or Sentinel satellite data. Detailed soil survey, which is required for the block level or village level planning, then we need a very detailed survey, 1 is to 20,000 scales or larger. And here we can use resource set satellite, list 4 sensor, merged with cartosat satellite data, panchromatic data, so that we can prepare a very detailed FCC, or large scale FCC, which we can interpret for the mapping of the soil. So if we want to prepare the soil map, then we have to first understand how these soils has been formed. So we can say that is the soil forming factors. This was given, the concept was given by Jenny in 1941, that it says that is soil is developed, or it is the function of 5 factors: climate, organism, relief, parent material, and time. These 5 factors, we can divide climate and organism as active factor. In climate, temperature and rainfall, and organism, various kind of land use, land cover, they provide energy to the systems. They are responsible for the weathering purpose or soil, leading to various soil processes. And these active factors act over the passive factors, means parent material, what kind of geology is there, what kind of landform is there, what kind of topography is there. Slope means what kind of slope. If slope is very steep, slope is gentle, then different soils will be developed. And these soils are how much old, means that we call it is a time period taken by soils from the stage of weathering rock to the stage of maturity. So, if we can summarize soil formation, how it takes place, here you can see the factors. Factors, as I discussed earlier: parent material, topography, climate, organism. These four factors, active and passive factors, they regulate or they govern the soil forming processes, means addition and losses, transformation and translocation, means a various chemical process which occurs within the soils because of these soil forming factors, and they developed properties, soil properties, which we can say morphological properties, which we can see with our naked eye, physical characteristics of the soils, for example, texture of soil, structure of the soils, porosity, bulk density, infiltration rate, hydraulic conductivity, they are the physical characteristics. Chemical characteristics, that is for the pH of the soils, electrical conductivity, cation exchange capacity of the soil, and soil nutrients, nitrogen, phosphorus, potassium, and secondary nutrients, calcium, magnesium, and micronutrients, and biological properties, means how much microorganism present into the soils, and biological properties which measure we considered in the soil survey is the amount of organic matter, how much organic matter present into the soil. So these properties are controlled, or these properties are arrived into the soils because of the soil forming processes, which is controlled by soil forming factors. And you are seeing the picture, that is a horizontal vertical cross section of the soil, where you are getting various layers, and we call it is a single soil, is a pad on. This picture you see the FCC, false color composite of Dehradun area, and here Dehradun city is this side, and this is the one hill, Shivalik Hills, and we can see here that is the FCC red color circled here. Both the places there are the red color. Here is also that red color is there. Although that is the red color you are getting because of vegetation, because these are the covered under the forest, and it gives the high reflectance in NIR band and low reflectance or absorptions in red band. So if you are NIR, you are representing as red color, so they are appearing red color. But all three places, color tone is same, but soil is different, because the parent material is changing, topography, slope is changing, and because of that soil is changing. Here it is in plain or foothills, here is on the hills, and here is the alluvial plains. So as the landform or geology is changing, soil is changing. So just by seeing the spectral characteristics on or seeing the FCC, we cannot say what kind of soil is there. So how we can see? So we have to study the soil forming factors. How I can study the soil forming factors? Then our task is to interpret soil forming factors using remote sensing data. So in this FCC, first we want to study the various soil forming factors. Here I can say, if suppose I want to prepare a soil map of this area, yes, in this area or in one district, you can say in that district or in a small area, climate is not changing much, and time is also not changing much. So both factors you can deny. They are not governing the variability in soils, so you can assume as a constant factor. So only three factors: organism, relief, parent material, they governs the variability in the soils. And we will see in the satellite data how we can interpret this thing, these factors. P means parent material. Parent material means I say the geology or geomorphology, and you can see I can interpret these are the hills, these are the foothills. So two type of geomorphology is there. And second is the topography. I can also, with the remote sensing satellite data interpretation, I can find out this is the very steep slopes, this is the steep slopes, undulating slopes, and gentle slope. All three, four type of slope also, or topography also I can interpret it. How I can interpret it? Based on the you can see the some dissection or drainage density. Here you are seeing the drainage density or dissection is very high. Here it is very less. Very less means gentle slope. Very high drainage density means it is a very steep slope. So some extent topography also I can interpret it from the remote sensing data. Otherwise, you have digital elevation model. You can also prepare the slope map with DM, and then you can use that information, or you can drop this satellite data over that, and you can get the information of slope. And third factor which is affecting our soil type is soil land, that is your organism, or organism you can see that is the land use, land cover. And from remote sensing data we can very well see, very well interpret the land use, land cover map. Where is the land use, land cover means this is the forest land, this is the crop land, this this light color, light red is a crop land, and scrub land where different bushes and that also you can interpret it. So I can generate the soil forming factors map, and which we can use for mapping soil. So that's why I am saying here that is the climate and time can be considered as a constant. And what we do in the soil mapping, we call it is the soil landscape analysis map. And here we how imply this function or soil forming factors. What we do, we go for the visual interpretation of satellite data, and first we interpreted the geomorphology map to prepare the parent material map. So first task is to or first factor which is governing the variability of the soil is your parent material. So first you prepare the geomorphology map, or you get the geomorphology map from any other source. Then this geomorphology map further divide each unit based on topography or based on slope. So if you are having two slope or three types of slope or four types, you divide each geomorphic unit based on your topography. Then third stage comes where we further divide that map unit considering the land use, land cover. Yeah, that is your called organism. And in that way, by systematic interpretation of remote sensing data, we can get the map unit or map area which we call it is a soil landscape map. So like that we are able to prepare the soil landscape map. And in the figures you can see this is the landscape, or suppose you can say the area you want to prepare a map, and you can divide the area of this one based on the your soil forming factors, which you are seeing the soil landscape map. This is the landscape map, and in this landscape map we are considering in each land unit area all soil forming factors are same. So you can take any place or any point soil observation, you can take the soil profile, and you can characterize the soils from top to bottom. And this is then each layer you collect the soil samples and analyze in the soil lab, and you can get the physical, chemical and biological characteristics of the soil. That is the basic concept for the soil mapping. And suppose you are not interested to map for the 2 meter depth. Generally, in the standard soil survey, we study 2 meter depth of soils, or the depth where we get encountered with the uh, parent rock or consolidated material in that one. But suppose you are interested for erosion mapping, watershed planning, or soil fertility, or soil productivity, or soil carbon stock assessment. So we need to study only the top 20 centimeter or top 50 centimeter of soil as per your objective. Then we can take samples of that area. Why you need to know the soil mapping procedure? Because most of the soils maps are available today are 30 to 50 years old, 30-40 years old, and soils has changed over the last year, last 10 or 5 years. And suppose for the nutrient point of view, nutrients or carbon point of view, so old map cannot be used at that case. So you can use this concept of soil mapping for mapping your area, dividing your area into various soil landscape unit, and in that landscape unit gives you a confidence that is you can take any samples from this area, which will any point in this land unit, any point that will represent the entire area. So it serves as a guidelines to collect the soil samples at in that area, which will represent for the entire land area. So that's why here I have shown the how to prepare the legend for interpretation. So you can say, I again repeating that first you get the parent material map, you or you get the landform types or geomorphology map, you divide your area into geomorphology classes. So first you interpret geomorphology of your area. So for example, hills, Piedmont plains, alluvial plains in the previous satellite data I have shown. Then you divide each map unit. Here I am taking only one map unit, one geomorphologic unit, hills. Hills can be further divided based on the topography, and you are getting these slopes. 3 slope classes I have divided and named it H1, H2, H3. And third level, now in each classes you further divide based on your land use, land cover. For example, steep hills into forest, scrub and agriculture. So we call it is 3-tier mapping approach. And so if you go systematically interpretation of your satellite data in this way, then at the end what you will get, the map area or map units, that map units are similar in soil forming factors, so you can assume that will develop similar type of soils. So direct reflectance characteristics of the soils doesn't give you the information of soil, but here you have to go the visual interpretation of standard FCC or remote sensing data, and you can prepare a soil landscape analysis map. Still I have not get the information about the soil, only landscape analysis I have done. Soil, unless I have not visit the area and collect the sample, then only I can attach the soil information, then it will be a soil map. So just for example, I am showing you, suppose this is the satellite remote sensing data, and I have taken that satellite data, and over that I have put the drainage map, because I tell you that drainage map help us to find out the slope of the land. If drainage density is high, then I can say slope is more. If drainage density is less, you can say the slope is less. And here I have taken digital elevation model also, where you can see that the blue color is showing the less elevation and red color is showing the highest elevation. So here is the high slope, here is the gentle slope. So topography can be interpreted from digital elevation model also. from drainage map also, and also with the drainage map. So you see, I have divided the, so again I am saying that you take one by one interpretation. Never do all three information together. First you have to prepare the geomorphology map. You see, I have prepared the geomorphology map, hill, foothills, floodplain, alluvial plain. Then second task is that I have to prepare geomorphology and topography map. So I have divided, suppose hills has been divided into three category or two category, H1 or H2, means steep slopes and moderate slope. Like foothills is divided into three, four classes. So then you complete the second information or second level of information, topography. Then you go for the third level of information, that is based on the land use, land cover. So again I have divided the, suppose hills further divided based on the agriculture, forest, that is. So now whatever the unit you are getting here, suppose this unit, entire unit soil will be same. So any point you can collect the soil sample and that will represent the entire area. That is the advantage, and this soil landscape analysis can be achieved very easily from the interpretation of satellite remote sensing data. Then what in the, if we want to collect the soil samples, then we take a transect or sampling strip considering the road crossing the entire area. So we do sampling both the side of the road, but away from the road, that is at least 100 meter away from the road, we take the soil samples. And in this, if you see that I have taken the soil profile study. In the hills you are getting stones, but when I come to the foothills, then you are seeing the stones are small size, coarse fragments, some stones are there, and soils are like that one. When you come, I come down below lower Piedmont, then soil profiles are like that one where you are not getting stones. And when in floodplains you are going, you are getting different type of soil. So unless exposing or taking soil profile, you can not get the information of the soil. Then we collect each layer, that is the horizons, the soil samples, and analyze in the lab. If you are not interested in the subsurface or lower layers, then top soil only can be collected up to 20 centimeter depth or 50 centimeter depth. So, but where to take soil samples? This soil landscape analysis will help you to tell you the location, to identify the location for soil sampling, and that location point samples will represent how much area, that also you will get to know. So this is the prepared the by interpretation the soil map. You get this is, these are the map units, and in these map units we have taken the soil samples and prepared the soil map. So this is the soil mapping procedure which I have explained you, so you can go through that. Then after preparing the soil map, then questions comes how to use that one, or how to use this map for land use planning. So we do the land evaluation. Land evaluation is a tool which is used to assess the potential of land or soil for suggesting the various land use types. It guides decision on land use. That means this soil is how much suitable for agriculture or how much suitable for forestry, or all these constant and potentials we can study. So what we do in land evolution, we are doing that is the, we suppose we, you have the soil and land characteristics, means from the soil map you get this information, and for the different land use, for example agriculture, for forestry purpose, for urban planning, you you know the requirements of that. From the literature we get this requirement. For example, for forest soils, soils should be deep, or agriculture crops, for paddy crops or wheat crop, requirements are different. So we can get the requirement from the literature, and then we compare the both, we match that one, and we can find out the suitability analysis. So it will assess the suitability, and that if you assess the suitability, then you can get the prepare the land use plan, and land use plan, then you can prepare the policies and plans for the area. So commonly we are using the land evaluation methods. Three methods in general we use. One is the land capability classification, which tells you that is the general suitability of land, means general suitability means a very it is suitable for agriculture or forestry, and if it is suitable for agriculture, then how much it is suitable. Second we can do, that is the soil and land irrigability classification. If the land is suitable for irrigation purpose or not, because if soil is not suitable for irrigation, and if you are doing irrigation, then in future there may be problem of some degradation. That's why we find out the land irrigability irrigability classification. And third method is your FAO, framework of land evaluation, that is used internationally throughout the world for the crop suitability analysis. This framework we assess used to assess the potential of soil for which crop we can identify. So if we see the land capability classification, you can define it is the, we generally assess the inherent physical potential of the land, and we, in this land capability classification, we divide the land into 8 capability classes, which are numbered as 1 in Roman numerals 1 to 8. If your soil is coming in class 1 to class 4, then we can say this land is suitable for agriculture or cultivation. If it is coming classifying under class 5 to class 8, then it means it is unsuitable for cultivation. It is capability classes we call it, and these classes can be further classified based on the limitation of the soil and land characteristics, and then we call it is land capability subclasses. And except first class, all classes can be classified in subclasses based on 4 limitations mainly. First is water limitation, means excess waters, for example wetlands. Another is climatic limitations is also there, for example arid climate and humid climate. Soil limitation means depth may be limitation of the soil, or texture may be the limitation, because if your texture is very coarse and very clay, very fine, then different kind of crops can be grown. And erosion means a degradation factor also taken into account. So you see the description of land capability classes. Capability class 1, 2, 3, 4. As you are going 1 to 4, your limitation for the agriculture is increasing. Capability class 4 is having the severe limitation for growing crops. It means you cannot grow all type of crops. But capability class 1, land is best suitable and you can grow all type of crops. Class 5 to class 8, if your land is classified in this category, then we can say that is capability class 8 has very poorly, soil is very less thickness, and soils are stony, and they doesn't support any vegetation, so we classify in capability class 8. And capability class 5, 6, 7 has the increasing the limitations in that soils. So how we can find out that land capability criteria, we have in the literature land capability criteria, and you have from the soil map soil and land characteristics, and then we match together by the by comparison, and we can find out the land capability classes. So, for example, a soil map which has been converted into the land capability map, and you can say the land capability classes are subclass with subclasses are given here, and it is saying that suppose you are saying that is the this is the majority of classes, class 7, these are the under the class 7 color, means brown color, light brown, and this land is suitable for only the forest but with moderate limitation, and capability class yellow, it is showing that this is suitable for the agriculture, and here capability class 6. So, different capability classes you are getting of the soil of your from your soil map, and that we can suggest what kind of land use one should practice on this one for sustainable development of area. That is it is the soil type, soil map was prepared, so it is shown that one. Okay. So, similarly, FAO framework of land evaluation can also be used for crop suitability analysis. Here I have shown up to the land capability map. Another that I have discussed the conventional method of soil mapping or standard soil mapping procedure, but today we are more on digital age, and we are working more on the digital soil mapping. So, here what I want to tell you that today we are using the digital soil mapping technique for the technique for the mapping of the soils, but strictly this is not as similar to the conventional soil mapping. Here we mainly focus on the mapping of soil properties, surface soil properties, and sometimes subsurface by establishing the relationship. So, what we do here, we are using one there we are using soil forming factors given by Jenny as a soil mapping concept, but here we are using Scorpion model, which is given by McBratney, defined by McBratney as a model for soil mapping, digital soil mapping. Here he defined that is soil is the function of this this that 4 factors were there, 5 factors. Here he has added one more factor, actually n factor, where n is, you can say, the geographic location or GPS location of the point. So, this method, other factors are remain same. For example, C for climate, O for organism, R for topography, P for parent material, A for time or age, but N is different, and this is given the Scorpion model. What we do in this one, we use that take the soil samples randomly spread over your area. You take the soil samples, but soil samples should be thoroughly spread on your area so that you can able to establish the relationship. You can generate then we take the covariates. Covariates means different maps. For example, digital elevation model, we can generate the different terrain attributes, slope, aspect, curvature. We can take the satellite data, we can generate various spectral indices, for example NDVI, soil brightness index, or many indices we can generate, and temporal data of remote sensing data is available, that also, and also you can add the geology, you can use the climatic parameter map. So, these parameter maps which is related to the soil forming factors are considered as a covariates, and then you take these maps, we use the statistical models, we call it the predictive models, and then we are able to generate the soil map. So, little more descriptions I can give you. In digital soil mapping, we are using the multispectral data for generating the environmental covariates. Hyperspectral remote sensing, if available, we can use digital terrain model, DM, we can use legacy data or old soil map, geology map, climate data, soil moisture, those maps also. So here your uh, aim is to get many more map, many more information, that is in the quantitative term, not in the qualitative but quantitative terms. And from satellite data we can generate the various spectral indices. There are 10 to 15 spectral indices can be generated, and that each map can be considered as a environmental covariates. So we use this as environmental covariates, and we are using machine learning methods as a tool. And in machine learning methods there are various tools are there or methods are there: artificial neural network, random forest, support vector machine, or deep learning techniques. These are so these techniques, they take the soil information from point map and environmental covariates, and then they analyze together using this machine learning methods, and then they prepare the soil properties map. Here we are able to prepare the soil properties, for example pH, electrical conductivity, carbon, CEC, NPK properties map, but not the soil map what I have discussed earlier for preparing in the conventional soil mapping. So here just I am showing you one example, that is how we can use this technique for the mapping of soil nutrients. You see that is here it is available your remote sensing data, satellite data, FCC. You can generate the NDVI map or spectral index. Here you have the digital elevation model, cartodem. You can generate the various terrain attributes map. Here you can say the primary terrain attributes, secondary terrain attributes, and these are the soil sampling points. I have taken the regular grids, soil samples of the surface soil properties, for example your nitrogen, phosphorus, potassium, analyzed in the soil labs, and these maps were integrated together based on the geostatistical techniques, where I use the co-kriging technique and kriging methods. Co-kriging where use the NDVI and terrain wetness index, secondary attributes TWI, and then we are able to prepare the total carbon map, nitrogen map, phosphorus map. So here you are by digital soil mapping methods, you are able to prepare this map. Instead of geostatistic techniques, you can also use the machine learning techniques to establish the relationship between the properties of the which you analyze in the soils of the different points, and of the same points you are getting the terrain attributes, or you are getting environmental covariates, and by analysis with the machine learning you can generate this digital soil nutrient map. Now comes that is the in the soil mapping you are using, also you have to map the degraded lands. And here in India, the total degraded lands are 120 million hectare, and if you see the country's total geographical area is 328 or 329 million hectares. So you can say one third of our country is degraded. And if you see the that is the agricultural land, arable land, 86% of our agricultural land is means karib, after out of 120, 104 million hectare, or that is 86% is agricultural land, and 14% of our forest land is also degraded. In India, if you see the ISRO and ICAR, Indian Council of Agriculture Research, they arrived an harmonized statistic that in India, around agriculture arable land, mostly it is affected by water erosion, 73 million hectare or 70%. And if you wind erosion in arid region in western India, you can say that 12% area is affected by wind erosion, 16% is affected by chemical degradation, that is your salt affected soils or salinity or alkalinity, and 1% is physical degradation, you can say the mining area, like that one, which is a deformation of the surface. So like that one, your country's statistic, mainly our country is affected by water and wind erosion and dominantly by water erosion. This is the map available on the ISRO Bhuvan site or ISRO SAC website, and you can get the map at 50,000 scale, soil degradation map of India, where you can find out that is the various kind of degradation, and you see the water erosion, the entire central India, which is severely getting affected by water erosion. And in alluvial plain or in Uttar Pradesh, you are getting salt affected soils. This one is the salt affected soils, and here also you are getting in the western India, that is the Rajasthan, Gujarat part, you are getting wind erosion. So, water erosion is the most important problem. Degrading our land. Can we map water erosion with your remote sensing data by visual interpretation? Yes. You see that this is the false color composite FCC or remote sensing data, and this is the, you are seeing the forest area, dark brownish red, and below that it is the foothills, and you are seeing the cropland. You see here the, you are getting a lot of gullies or drainage channel, actually they are also called as a gullied land, and you can see lot of dissection of the lands is there. We are characterizing it is very severe erosion, and below that one you are getting less gullies but wider gullies, but less than that one, so it is the severe erosion. And below that one you are getting no gullies, not much gullies are there or few gullies are there, but generally the top soil is removed, and top soil is removed, then it becomes only sand particles, or because of water erosion what happens, fine particles, clay and organic matter is removed, wash out from the surface, and the coarser material and sandy materials are left into the soils, that gives the high reflectance. So that's why you are getting the high reflectance here, and it is the moderate erosion. And here if you see, you are getting little good reddish color, so it is because of vegetation or crop, and the crop is performing better than this area, so you are getting the slight erosion. And here you are getting the very good crop, and here you can say there is no erosion. So we can map relatively if we know how soil erosion, which are the soil erosion factors are there, how they are governing. If these concepts we are there, we can interpret remote sensing data for also for soil erosion mapping. So we can map the sheet erosion, we can map the gully erosion, we can map the dense gully erosion. So E1, E2, E3, 4 you can map here. What are the factors which is governing the soil erosion? It is described here in this equation, that the soil erosion is governed by R rainfall, K soil erodibility, K factor, LS factor means topography, L means length of the slope, and S is slope steepness, and CP is the cover and management practices. So these 5 factors are there which governs the erosion in your area, and these factors we can interpret it in your remote sensing data directly, and we can map the erosion classes by visual interpretation methods itself. Now comes to the salt affected soils, which is the another kind of degradation occurs in our country, that is the around 12% area is affected by that, and it is mainly in the irrigation command area, where we are irrigating to get the more yield, but at the same times that area is also getting converted into the salt affected soils, And here you see the ground picture. It is in Mathura district of Uttar Pradesh. You see on the surface, lot of salts has been accumulated because of high evaporation rate. And you see this salts on the agriculture fields in the month of May and June. You can see that one, April, May, June. So satellite data was taken of April month, and you can see the salt salts appearing as a whitish tone in this one. So you can easily map the saltwater swells. So I told you in previously that degraded swells we can map directly with the reflectance characteristics because of there is a change in the surface characteristics as compared to the normal swell. Here at the same places where saltwater swells are there, you will also get the waterlogged area. You get the water on the surface, and that will appear as a bluish in tone, bluish tone color. So these are the waterlogged area. So we can easily map the salt affected and waterlogged area using satellite remote sensing data. And this is the spectral characteristics. You can see that is if the highly salt affected swells gives the high reflectance, and low salt affected or low salinity gives less, and normal swells gives like this spectral characteristics in the multispectral band. Now we can also use for mapping of the salt affected swells with the digital techniques, or where you can use the supervised classification. This is the study shown in the Rohtak district of Haryana. This is the district has been masked, and you see the whitish color. These are the salt affected soils, and these are the waterlogged area. So on the ground, these fields appears like that one, and by classification you can map that is where you are getting the yellow color, yellow tone. We have given this is the salt affected soils, and you can map that is the waterlogged area. Here these are the waterlogged area. So we can easily map this degraded lands using remote sensing data as a digital method. For degraded lands or in salt affected soils, I want to show you how we can use the hyperspectral remote sensing data. So if you see the multispectral, suppose Landsat data, it is shown that is you are in the different bands, you are getting the reflectance characteristics like that one. But in hyperspectral satellite data, you are getting the spectral signature, more better characterization of the reflectance. So it used mainly for the quantitative mapping. So you can say the multispectral data used for the qualitative mapping, where you can say the slight, moderate, severe salinity, the salt affected soils. But here you can study the hyperspectral data for the quantitative mapping of the pH of the soils, electrical conductivity of the soils. So just one example, I will show you a case study in the same area in Mathura district. We have taken the hyperspectral remote sensing data, and we have prepared the various spectral indices using the spectral hyperspectral bands, and we find out the which spectral bands is most sensitive for the chemical characteristics of the soils, and electrical conductivity, pH, EC, ESP, SAR, these are the chemical characteristics of the salt water soils. And we found that salinity index is the most important index which can be used for mapping these properties. So salinity index and brightness index, we found two index are very important, and we prepared the identified the spectra of soils also, and then we can map the soils with the different that is different electrical conductivity EC values. So this electrical conductivity values, if we know, then we can make a better reclamation program, or planners want to know that which soil having highest salt content, which is have the lowest. So you can say these are the soils where the highest salt concentrations are there. So we can accordingly we can go for conservation planning or improvement of the soils. So thank you very much for your kind attention and listening these lectures. Here I am giving you one link which you can see there, https, and this link you can type in your Google Earth, or in your computer, and you can download this book, Earth Observation for Soil Resource Assessment, which you will get in a very briefly described the different aspects of the soil resource assessment, soil resource mapping, land degradation mapping, soil quality mapping, and various chapters where you can, how remote sensing data can be are being used. Thank you very much and wish you all the best. And now I am available for your question, if any there. Okay, so now I take the questions raised by participants. One is that can remote sensing GIS help in mining gold, diamond, or other valuable elements in a steep slope? I have not covered these things, but remote sensing data are very well used for the mapping of different rock type, geological material. So, if you are mapping the rocks, and then you can map the gold mine area also. So you ask these questions, or you will get the answer when you will have the lecture on remote sensing application for geological studies in coming days. Another question from Arju Kumar. How does a rock such a granite transform into completely different type of rock? So this is not the questions related to my lecture. You ask in geological remote sensing in geology lecture. कोई क्वेश्चन तो दिख नहीं रहा.